Okay, so in this video, let's talk about how efficiently we can implement the quantum Fourier transform. Well, this is the quantum Fourier transform matrix. It's actually also in classical computing, it's known as the discrete Fourier transform. Now, often when we talk about the discrete Fourier transform, we don't have this normalizing factor 1 over square root n. But in any case, the input to the discrete Fourier transform is a vector. It's a complex vector which has dimension capital N. And the output is also a complex vector of dimension capital N. And so normally when you do this product of a matrix times a vector, how would you do it? Well, for each entry beta j, you would take this column and you'd multiply it by the jth row, which requires you to do capital N multiplications and additions. So it takes roughly n time, but there are n such entries that you must compute. So you imagine that this should take you order n squared time. So the fast Fourier transform algorithm, which is a remarkable algorithm, so it's called the FFT, it does it in order n log n steps. It's a nearly quadratic improvement. And this is a very, very significant improvement in classical algorithms. This improvement from n squared to nearly linear time, this is what's responsible for these, this is basically the algorithm behind digital signal processing. It's the algorithm that's used in your iPod or your, just almost every form of digital music and video and so on today. So it would be hard to imagine the modern world without the FFT algorithm. Okay, so that's on the classical side. Now, how much faster can we do all this quantumly? So to understand that, let's first understand how we present our input in the quantum case. Let's now think of this as the quantum Fourier transform. And let's think of capital N as a power of 2. So write it as 2 to the little n. So now we think of this capital N dimensional vector as the state of little n qubits. So that's this exponential compression that we get with a quantum system. So the state of this little n qubit system is really this superposition, this exponentially large superposition. And so now what we are going to do is we are going to input this into a quantum circuit. And it's going to output these n qubits, but now in a new state. And in what state? So they start off in this state, and once we are through with the circuit, they end up in this state beta. Okay, so the input state is summation alpha j. The output is summation beta j. Okay, so now what we'd like to know is, how big is the circuit? How many quantum gates are there in it? That's a measure of time, the time it takes, or the complexity of carrying out this quantum circuit. And it turns out that the complexity of this quantum circuit can be made as small as big O of n squared. This is what we'll see in one of these next few videos, maybe in the next lecture. And if you work harder at it, you can even make it close to order n. So you can even remove the square from the exponent. But now, how big is little n? So if capital N is 2 to the little n, then little n is log of capital N. So this is like big O of log squared n. You could also reduce it down to log n, but in either case, This is an exponential improvement. Okay, so remember I said going from n squared to n log n was a remarkable achievement. It has, it has changed the world we live in. Whereas quantum computing gives us this exponential improvement. Now where's the catch? So there's a catch. So the catch is that classically when you compute the Fourier transform, you give this complex vector as input, you get the complex vector as output. So you get all these capital N numbers, beta naught through beta n minus 1, as output. What happens when you do this quantumly? You have the state of this little n qubit system, you process it using the quantum Fourier transform, you get a new state of these little n qubits. But that's the private world of nature. That's in the superposition. You don't get to see these complex amplitudes beta naught through beta n minus 1. So what do you actually get to see? Well, when you measure, all you get to see is some random j, an index j, with probability beta sub j magnitude squared. Okay? So you don't get to see the beta j's, you don't get to see all the beta j's, you don't even get to see one of the beta j's. All you get to see is an index j sampled according to this distribution. Okay, here's Fourier sampling again. That's what you can do. You can compute this enormously complicated object. That's what nature does for you. But then you don't get to see it. You only get a sample from it. And this is the main issue in quantum algorithms. How do you make use of these extremely powerful primitives where nature is doing something extremely powerful and then refuses to share with you most of what she's computed? So what nature is willing to do is just give you a little hint, just the index j. How can you use this information? Okay, so there's a story that's sort of reminiscent of this. Gordon Moore, who was the founder of Intel, after whom Moore's law is named. So he observed back in, I believe it was back in 1965, that the number of transistors in a chip had been doubling every 18 months. And he predicted that this trend would keep going on. So he noticed it for the previous 8 to 10 years, and he predicted that this would keep going on quite indefinitely into the future. Now, there were other aspects of this kind of exponential scaling. If you keep doubling every 18 months, that's an exponential increase over time. There were other aspects of this exponential improvement that was being noticed, in terms of processor speed, in terms of costs of computation dropping at that exponential rate. And that's what's responsible for this remarkable computer revolution we're going through. But Gordon Moore was once giving a lecture about this, and to illustrate his point, he said, well, let's imagine that the automobile industry had been on a similar trajectory since the mid-50s or the 1960. Then he said, well, by now you could buy a Rolls-Royce which would consume a gallon of gas for something like 10 million miles. It would travel at 1% of the speed of light. It would cost under a dime. And then somebody in the audience piped up and said, and it would be as small as a matchbox. Okay, so that's what we see with this quantum Fourier transform. You have this incredible improvement in performance in almost any measure, and yet the results are so small that it becomes hard to use. Okay, so in the next lecture, we'll see how we actually make use of this information.